Well, we can really understand amplifiers and the way things are. We have to understand something called impedance matching. Y'all heard of this before? Yeah, and this is explained a little bit, and so here's our power formula. Here's our formulas, right? Ohm's law. And these are our power formulas for DC, single phase AC. This is our power formula for three phase, by the way, which we don't know much. And you also know that. So this is three phase. It's sitting over three wires, but actually adding a second wire, we get times the square root of 3 more power out of it, just by adding another wire and another phase. So three phase is really efficient to transmit over single phase. Conductors are used to deliver power communication signals. Similar to power delivery system, electrical sending information requires two electrical conductors. In DC, the opposition to current flow is set by the resistance of the source and the return conductor along with the load. In transistor amplifiers, we have two oppositions that we're going to look at, and this is what we call the input resistance or impedance and the output impedance of the circuit, which is what we really need to understand. In AC circuits, the opposition is set by something called resistance and reactance. So resistance, this is what you learn in DC, right? Let's throw another slide in. All your formulas you learn in DC basically deals with resistance. But you notice my formulas have changed a little bit. So back in DC, you learned that V is equal I times R. Well, I'm not saying I times R. I'm saying I times what? Ohms. And I would be, you learn I is equal to V over R. I'm not saying V over R. I'm saying V over ohms. Well, that's what we're fixing to talk about. Well, see, what we have, and I don't know why this ohms is bigger than the other ohms, but anyway. Can that be the same ohms? No, it's not. It's not. Because what happens in AC, we end up with two devices that are reactive. So we have capacitors, which we played around a little bit as being filters. These guys have an opposition, and the opposition is ohms, but it's not resistance. If I took an ohm meter and put it across across a capacitor, it's going to show, if it's a small capacitor, it's going to show infinity. I put it in an AC circuit, it's going to have ohms. And then we have inductors, which is a symbol of a air core inductor. I measure this with an ohm meter. I put it in a DC circuit. The dang thing acts like a piece of wire. I put it in an AC circuit, then it has an opposition to the AC that we call reactance. So the formula for X of L is 2 pi FL, and the answer is in ohms. That's opposition, but it's opposition to AC. It's not opposition to what? DC. The formula for capacitors is X of C, which is, we call it capacitive reactance, by the way, is 1 over 2 pi LC. So notice this. So I buy inductors by this right here. This is called inductance, and it's given in units called henries. And of course, capacitance is given in units called farads. So when you buy a capacitor, you go out and you buy a resistor, you say, I want a certain ohm resistor at this wattage rating and this tolerance, right? You go out and buy a capacitor, you say, I want a 100 microfarad capacitor. Because the problem is its opposition changes with what? Frequency. So that means as frequency goes up, a capacitor's opposition goes down. And if frequency goes down, the opposition to the capacitor goes up. So this is why if I use DC, it has 0 ohms. It has infinite resistance. So that's why when you take an ohm meter and measure it, because your ohm meter puts out DC. So when you put your ohm meter across a capacitor, it measures infinity because you have no frequency, right? You understand? I take that same capacitor and put it across 100 hertz, and then it's going to let information flow. It's going to let things flow through. So one of the features that we've learned about capacitors is one thing is they pass AC depending on the frequency. And the second thing we learned is these guys do what? They block DC. So it allows us to take an AC signal, if I choose the right capacitor, take an AC signal and couple it into a DC circuit. So the problem with X sub L and X sub C is and this guy, X sub L, if frequency goes up, its ohms does what? Goes up. If frequency goes down, its ohms goes down. So no, they're different, right? You understand that. So the big thing about, we say an inductor passes passes DC, because all it is a piece of wire, and then it blocks AC depending on the frequency. So we've got two devices now that vary their opposition with what? Frequency. And what's the nice thing about capacitors and inductors is they're exactly opposite of each other, so that if you get them in a circuit together, they cancel. If you choose the right sides, they will cancel themselves out at a certain frequency. So we use these for what we call filters, that are frequency components. So anytime I have C, so as soon as I come over here, and I come over here on my input, and I put that thing right there, and I put that right there, then we got X sub C involved in this, which means it's going to drop a voltage. This is why every amplifier has what we call a lower cutoff frequency, which means they won't handle real low frequencies, right? Because we have to couple it in with capacitors. As soon as I put that capacitor in there, then it changes the term. Impedance. So in AC circuits, we have both resistance. This is R, right? You'll understand. And then we have something called reactance. Reactance is devices that change their opposition with frequency. And impedance is the opposition of flow in an AC circuit that contains both resistance and capacitance. So we should be talking about input impedance and output impedance because we have a capacitor out there, right? You understand that? Note that in most amplifier and communication systems, all types of opposition is called what? Impedance. So you'll hear that term all the time, even if it's nothing but a DC circuit that deals with communication. But communication and amplifiers, we don't usually amplify DC. Usually we take and amplify AC signals, right? You understand? Are you okay? But to some degree, everything opposes the flow of electrical current. A regulated AC or DC power source appears to have an impedance of practically zero as long as the power supply's design parameters are not exceeded. So as soon as we stuck that Zener in there, the output stayed basically constant, right? You understand? Because the Zener is changing its current or changing its resistance to regulate as long as you don't exceed the design parameters of your amplifier. Of your regulator. Every AC and DC signal source will have some internal resistance or impedance. The internal impedance causes the voltage provided by the source to drop when the load is attached or disconnected. So what I've got up here is I got my signal source, which is my function generator. And what I'm going to show y'all is we're looking at this. All I'm going to do is I'm looking at the input of my signal source, and I'm going to come up here and disconnect it from the amplifier. Y'all can see that? And what do you notice about the yellow one? Oops. Oh, wrong thing. Yeah, it is. What do y'all notice about the yellow one? It went up because I unloaded it, right? You understand? As soon as I load this thing down, the actual output of the function generator dropped because this is not a regulated output, right? You understand that? Plus we're running it through a pot. So what determines, so every time I'll take a signal coming from my antenna, as soon as I hook it up to an amplifier, it puts out less voltage. Why? Because it's loaded, right? You understand that? An internal impedance causes the voltage provided by the source to drop when the load is attached. Power is work, not voltage and current. We can't have power without voltage, and we can't have power without current, right? You understand? But what we're concerned with on amplifiers is we're not concerned with a voltage gain, and we're not concerned with a current gain, even though we have to get that. What we're looking for, every amplifier should give you a watt. So what does it amplify? Power. Y'all understand that? Now you got to understand. I keep telling people this: is all your power comes through this guy we've been talking about most of the semester, called a power supply, right? You understand? So amplifiers don't create power. All they do is manage the power available from an amplifier. The primary goal of an amplifier and a communication channel is to get the maximum power transfer between the source and the load, right? You understand that? Power transfer between the transmitter and the source and the receiver in a circuit is maximum when the impedance in the circuit's matched. Every signal transmitted has some impedance that will cause the output of the source to drop when it's connected to a load. The example on that slide. So this is what we're going to deal with. We're going to deal with DC. We're not going to deal with AC right now. We're going to deal with DC. So what I've got is I'm going to come over here and I'm going to have a circuit that's simulating a signal source. And every signal source has an internal impedance, right? You understand that? What's nice about the function generator is it tells you right below it, it says 50 ohms. So that function generator's got a 50 ohm output impedance. And what we're going to do is this signal source, this is not a regulator, this is a signal source. Every one of them has an internal impedance, which I'm giving you as what? 100 ohms. And what I'm going to do is I'm going to come out here and put 3 loads out here. I'm going to put a 10 ohm load, I'm going to put a 100 ohm load, and I'm going to put a 1,000 ohm load. Now guys, we could go with milliohms, but we're going to just do these 3 so we can actually see what's going on. Now what we're trying to do is we're trying to get maximum power to the load. So this guy I'm going to connect over here. So when will I get the maximum power? Would it be with a 10 ohm load or a 100 ohm load or a 1,000 ohm load? Who says a 10 ohm load? Milton says. Who says a 100 ohm load? 2. Who says a 1,000 ohm load? And Anthony didn't vote. Got to vote. What do you think, Anthony? Okay, so it's 3. So let's do the math. So we'll come up here and we'll slap a 100 ohm, 10 ohm resistor there, and we're trying to calculate how much power is getting to the load. So first of all, I need to know the voltage across the load, right? So I use my voltage divider formula. So I said DR, we'll call it RL, would be equal to 10 divided by 110 and times 10, that's our load. And then what I'm going to do, guys, I'm going to come up here, I'm going to take this answer right off the bat, and I'm going to square it. And then I'm going to divide that by 10, so we can do this with one whack. So what I'm using is I'm using this power formula that says what? Power is equal to V squared over R. So we can do this with basically one whack, right? One nice little formula. So 10 divided by 110 times 10 equals, square that, divide by 10, and this will give us our power for 100 ohms. Milliwatts. That's 3 milliwatts. Are we okay? So what we're going to do is we're going to come up and we're going to put that 100 ohm resistor in here as soon as I get it right. Here we go. I don't know why I keep doing that. Let's calculate the power here to the 100 ohm resistor. So y'all got the formula down, right? Pretty straightforward. $250 milliwatts. 250 milliwatts. Now we put the 1,000 ohm resistor in there. What would be the power? Is 1,000 ohm. 82 milliwatts again. It's the same ratio. And we could come up here and we could do it in tenths of ohms. We could do it in hundreds of ohms. We could do it in thousands of ohms, guys. And what we would find out is you get maximum power transfer between the source and the load if their oppositions match. If they don't match, you're not getting maximum power transfer, right? You understand? So that means I wouldn't want a low impedance source feeding a high impedance load. I wouldn't want a high impedance source feeding a low impedance load, right? You understand? So I'd like a low impedance load. I'd like to get it as close as I can, but generally speaking, that's what we're looking for. Now in communication systems, we match everything. So when you come up here, you look at the different types of cables we use in communication. We either use come on guys. We usually use what we call a twisted pair cable. These guys are we use coax. Most of y'all are familiar with coax cable because this is what your cable TV, if you got cable TV, or even if you got DirecTV with that antenna on top of your house, they run coax cable down there. And what this is, guys, this is not a DC impedance. This is an AC impedance. So coax cable, we get 2 times. We got what we call an RG58, which is what we used to use in networking. It's a 75 ohm cable. That's the impedance of the cable. Not the resistance, the watt. The impedance, you'd have to put, it's rated at 100 megahertz. So if you put 100 megahertz on this thing, it would represent 75 ohms. What we use in your cable TV is the RG59, which is a 50 ohm cable. Now, if you measure between the center conductor and this with your ohm meter, it's going to measure infinity, right? You understand if it's not connected to anything. You put a 100 megahertz load on that thing, it's going to represent 50 ohms. So that means in my communication channel, if my amplifiers have 50 ohm outputs and my cable has a 50 ohm and your input on your TV has 50 ohm, then the impedance in the entire system matches and you get what? Maximum power transfer between the what? The source and the load. So this is why if your cable breaks and you come up here, my father-in-law did that before he passed away. He was driving a truck, big old truck through his backyard and got hung up on his cable and broke his cable. And then he got out there and just twisted the wires back together and taped them up, and he couldn't understand why he had such a crummy picture because he screwed up the impedance, right? You understand? These guys, depending on the number of twists you have and per inch, these guys act like a little capacitor. So, and these act like little inductors. So this guy we call these twisted pair cables, and this sets the what? The impedance of the cable. This is 100 ohm. I think it's at 10 megahertz. I'm not sure. I have to go back and look. So you can't, when you're splicing this stuff and terminating, you can't untwist that thing a certain length, because if you untwist it too far, you screw with the watt, the impedance of the cable. So when we get into an amplifier, what we're concerned with is the impedance of the amplifier. So, so what's the input impedance of the amplifier? So here comes my signal. And of course, we're going to have some type of plus DC up here. Right, understand, this is a NPN transistor. And my signal comes through. What does it see? Now, we're not doing current flow, we're doing signal flow. It makes it a lot easier so we can see the path. So here comes my signal from the input. So I can come over here and have AC. This over here is DC. And I can couple my AC through this capacitor, because what's their general rule of thumb? It does what? Blocks what? DC, and passes what? AC. Now we're going to use a pretty good sized capacitor there, either 100 microfarad or 10 microfarad. We're not going to use any picofarads because it will have a lot of opposition to my AC. So here goes my signal. We know it goes this way, right? You understand? Everybody okay? Then what does it do? It goes this way. Then it goes through the transistor, and then it goes this way. So that's my equivalent circuit. So basically, if I drew my equivalent circuit, if we're going to call this R1, we're going to call this R2, this is R2, this is R3, I'm sorry, this is R2, and then here's my transistor, and this is RE. RE, from this point of view, we looked at that, is seen, RE is seen as times beta. So that's why we basically ignore it. So this is my input resistance. So this is what our input impedance. This is what I would do. I would make sure I choose a capacitor that was big enough so it would allow the frequency I'm trying to amplify to come through, right? You understand that? Yes or no? So what frequency can the human ear hear? What frequency? Y'all, you don't hear sound, guys. You hear frequency. You hear vibration that's occurring in the frequency, right? You understand that? So what frequency range does most humans can detect? Less than a dog, right? On our upper end, but what's the lower end? I don't know. The low end, no, dogs don't hear dogs, they have extremely good hearing in high frequency. We usually round off around 15,000 hertz. Some people's a little better, some people's worse. Depends on high frequency. Yeah. So they have a lot better high frequency response than we do. That's why you can buy that dog whistle and blow it, right? So we could figure this out. When we take a break, I'll go and get a speaker and we'll hook it up to this function generator, and I'll start off real low, and then I'll do what? Go real high until y'all can't hear it. You can't, yeah. It's there, but you can't hear it because your ears just don't respond to it, right? You understand? Yeah, well, they can hear it a lot higher than we. That's why you can buy those dog whistles. You blow on it to train the dog, and people just say, "What are they doing?" So usually around 30 hertz. Around 30 hertz is our low end, and then around 15,000 hertz is our high end. So all your audio is somewhere between that range, right? You understand that? Now my output circuit, this is where your output is developed right here. So my output is going to be equal to this resistor right here, which we'll generically call RC. And if we choose the right capacitor, we can ignore it to calculate the output impedance. And then this right here would be the load that I'm going to drive this thing with. And this would be the way I would calculate my output impedance. Everybody okay? So what we're saying is that I wouldn't want an output impedance of 15 ohms driving an input impedance of 10,000 ohms. Right? You understand? Because I wouldn't get what? I wouldn't get maximum power transfer. So I wouldn't want a low impedance source to drive a high impedance load, or I would not want a high impedance load source to drive a low impedance load. And that's why we're really trying to figure out this stuff. So engineering these amplifiers are going to be very, very complicated, because you have to not only take in how much gain you need, but you also need to take in what type of resistance this guy's going to feed. So what we do is we might have another amplifier over here driving what? Driving this amplifier right there. So what we're trying to do is we're trying to match this output impedance of this guy with the input impedance of that guy, right? You understand? So it starts getting pretty complicated, especially when you're dealing with standard resistors. Huh? Oh yeah. You had never seen them blow the whistles? So guys, let's come up here. This is the amplifier I have hooked up here. So this would be so this is the amplifier we have hooked up here. This is a 100K. This is a 10K. RC is a 10K. RE. Y'all go back and let's calculate this.
What amplifier?
Here's the transistor right here. Here's my plus coming out my power supply. Here's R. This is RC. This is R1. This is R2. This is RE. And then these are my coupling plugs. Okay. So let's go back and calculate this, guys. How much volts? Got 12 volts. And this is a 1K. So we need VB, VE, BC, BCE, and then our gain, our approximate gain. Well, we can do it looks like it's got a gain of 10, right? Huh? Yeah, VB. We know how to calculate all this garbage. So these are the ones. If I was troubleshooting, this is what I would measure. I'd measure VB. I'd measure VE. I'd measure VC. I measure voltage collector to emitter, and that would tell me everything I need to know about this amplifier. And what's neat, guys, we're going to leave the AC signal hooked up to this, and we're going to cause some problems so we can see what's going on with our bias. So anybody got VB yet? So VE would be what? What's that? 400 millivolts? I thought you said 100. Then we can use VE to calculate IE, right? And we use IE to calculate VC. Anybody got VC yet? We got 400, I think. 1.1 minus 7, minus 0.7. Oh, sorry. Yeah, that's why the that's right. It wasn't a 1K, it's a 10K. So what do we get for VC? Eight volts. So voltage collector to emitter. And the gain is going to be about 10. So this guy here is operating toward cutoff. So that means if we raise the input signal, it'll clip on the top before it clips on the bottom. So let's see how good y'all did. So here's the meter. So here is ED. About 1 point. Yeah, pretty good, right? So here's VE. 390 we figured is going to be 400, right? Here's VC. 8 volts. Okay. Now this is my input signal right here. So we're bringing in. Oops, I didn't want to explain that. So we're bringing in 50 millivolts per division. And let's adjust this so it's going to be equal, so we can measure it pretty easy. Okay, that's good. So what's my input signal? I got it on 50 millivolts per division. Can y'all see my divisions? 1, 2, 3, 4, 5, 6, 7 divisions. What we got? Yeah, 50 millivolts per division. I don't know if y'all can see that or not. There it is right there. Well, your scope measures peak to peak, so that's what we're calibrating peak to peak. We're not worried about RMS because I'm going to use my scope to measure peak to peak out, right? You understand? So what we got, our input voltage? Understood. 7 times 50 millivolts. 350 millivolts in. Now what I'm doing is I'm looking, this is my actual input, but I'm going to do this on, so this is AC. So here's my 0. I shifted it just a little bit. No, the blue is the output. I'm not using it right now. So this is AC, right? Okay. What I'm going to do is I'm going to move it over to my actual base. And what we're going to do is I'm going to make sure we got it on DC. I'll let y'all see exactly what's going on. So here's channel 2. We're not on that yet. But what's actually happening is here's 0 now, right? Y'all see 0? And so this AC signal is riding on. So what we did is we brought that through the capacitor. So I had AC on the other side of the capacitor. Now what the AC is doing is adding and subtracting from my base voltage, right? You understand that? So it's actually riding on top of DC, our base bias voltage. Here's my output. This is on the collector. And what this is doing is this is allowing the collector to change, right? You understand? So we're changing the DC voltage, but we're changing it at an AC rate, right? You understand that? So what happens is that this allows us to bring an AC signal. So this allows us to bring an AC signal over here on this side. So AC over here. Over here, this is going to be, if this is 0, that same AC signal is riding on top of DC. So what it's doing is adding, subtracting from the DC base voltage. If it adds and subtract from the DC base voltage, it's going to add and subtract over here on your emitter resistor, right? Which changes the current flow, which just causes the output flow. This is sitting here at a DC. This is sitting here at 8 volts DC. So what is happening is we're changing, when this thing turns on, it's changing the DC level. Then after we bring that through a capacitor, what is the capacitor doing for us? It's blocking the DC bias and letting the AC signal come out, right? You understand? So the amplifier is a DC amplifier, right? You understand? But it appears to amplify AC because we're doing it what? We're coupling it through a capacitor. So what do we call these capacitors? Yeah, they're called coupling capacitors. Now, odds are, when you get out here and look at these things, you're not going to have to calculate them, hopefully. These voltages are going to be given to you. But now you understand where they come from, right? You understand. And we know this is not a real good amplifier. Why? because I got 12 volts right here, and I'm setting this sucker at 8, right? You understand? Where would we like it? Where would we like DC to be at? We'd like it to be at 6. So I could do one of two things. I could increase my bias base voltage, which would cause my current to go up, which would cause this resistor to drop more voltage, right? You understand? Or I could change the size of these resistors. What I'm shooting for is I'm shooting to match the impedance of this guy over here. So basically what we would like to do is we'd like this right here to have 10K ohms worth of impedance. That's what we would want. But it's going to be highly unlikely, right? You understand? But I wouldn't come over here and run this thing off a watt into a 100 ohm load, because now RC is going to drop so much voltage, we're going to get so little power over there, right? You understand? It's pretty neat. Are we okay? So let's go over here and we'll switch over, and then what I'm going to do is I'm going to move over on the other side of the capacitor. So I'm going to take my input and put it on the input side of the capacitor. Now it sees it as AC. I'm going to take my channel 2 and put it across out on the output capacitor. And now it's seeing AC too. So what I can do now is I can come over here and start turning these things up. Just put them on top of each other. I'm going to put it on the center line. And what's wrong? We're out of trigger, right? You understand? Yeah, so we need to find our trigger. Here it is. I think we got to set the trigger on channel 1. So now we can measure this. So this is still 50 millivolts per division. This is a half a volt per division. I'm going to move this down. We know we got, what did we say? 350 millivolts coming in. Okay, so I'm going to take my green one. It's on a line. So it's on, so I got 1, 2, 3, 3.5 volts. 3.5 volts out. 3.5 volts out. 350 millivolts in, huh? That's exactly a gain of what? 10. Pretty neat, right? Of course, the problem is we're not getting any work out of this thing because we're not running a watt. We're not running a load. So I got a 10K load over here, so this should match us up. So as soon as I come up here and hook up my load, my output should drop down because now the amplifier is loaded, right? So what we would do to figure out our gain now is I would take 10K in parallel. So now it's going to be 5K divided by 1K. So now we should expect a gain of 5. Y'all understand that, or did I go too fast? 10K in parallel with 10K. So what we're doing, the actual formula is actually Z out. So we represent impedance by Z, by the way. So the true formula should be Z out over RE. But, you know, right now, R out looks good because we ignore the capacitor anyway. So R out is going to be this guy here in parallel with that guy right there. So 10K in parallel with 10K would be equal to 5K, right? And then that would be over 1K. And what does the K's do? Cancel. So that means we're going to have a gain of 5. So let's check and see if we have a gain of 5. So we know we're getting 350 millivolts in. So I'm going to have to move my blue down a little bit so we can get it on a vertical line. In fact, let's drop it down so we can get a really good measurement. Oops, one finger. Ooh. So that's 10 millivolts per division, 200 millivolts per division. 1, 2, 3, 4. So what's that now? So we're still putting 350 millivolts in. If I multiply that by 5, what would that give us? 1 point what? Okay. So this is 200 millivolts per division on my output. I'm sorry. So this would be 1, 2, 3, 4, 5, 6, or 200, 400, 600, 800, 1, right? You understand? 1.2, 1.4, 1.8. We calculated we're going to get 1.75. And it might be 1.75. It looks like it's down just a hair, but 1.8 was easy to measure. Are you okay? Okay. Now, watch what happens. Let's turn this back down. And what we're going to do is we're going to raise the input. Now look what started clipping first. Can y'all see? The tops. Because what happened is that we only had 8 volts to work with, right? So we're moving, so cutoff moves it toward 12. Once I get up to 12, the transistor watt is cut off. And then eventually what will happen is we probably can make the bottoms clip too. But we call this distortion. I can't get it. 8 volts, we don't have enough to work with. Okay, guys, y'all take a break. Huh? I ain't got the final exam schedule yet. I sent an email to Dr. Davis. If you look at the Galveston State website, they still have it for summer. And I can't remember what it talked about. And it should, yeah, RN. DN, yeah. Now, generically, we call these, for formula sakes, we call this R1, R2, RC, and RE. But in real life, they're going to be anything, right? But we got to come up with a technique where I can set y'all up a formula. So it should say RN would be equal to R1 in parallel with R2 in parallel with RE times beta. The typical beta for a 3904 would be 100. So what would be RN? What would be RN? Or ZN? We're ignoring the capacitor, and this is what the engineer does. They size the capacitor so the frequency, we can ignore the capacitor at the frequency that it would do. So if this is 100 microfarad, which is what I have, then X of C would be equal 1 over, let's say 30 hertz. What resistance or opposition, or not said resistance, what reactance would it have at 30 hertz? So that's going to be 2 pi, which would be 3.28, I'm sorry. 6.28 is usually what we use for 2 pi. times the frequency, which is 30 hertz, times 100 microfarads. And then we take the reciprocal of that answer. That would give me the impedance of this guy at 30 hertz. Yeah, only 53 ohms compared to this input impedance right here, which is going to be slightly less than 10K. So 10K, 53 ohms relative to 10K is nothing, right? You understand? And if the frequency goes up, the X of E goes down. So at 10,000 hertz, this guy would have almost no impedance at all, right? Or no reactance at all. So if we choose the capacitors, these coupling capacitors, what we normally do, if the amplifier is designed correctly, and when they give you the frequency response of your amplifier, that's what they're talking about. Those capacitors are designed to let the low frequency through, right? At the amplifier's rate. So what do y'all get for Zn? This is this formula came from where? Came from DC. The only thing we've added is the emitter resistor is seen as times beta. It's just the reciprocal of the sums of the reciprocal formula. I would start over here, guys, because do that one first. Say so I'm not going to write 1K. I'm just going to go over here and write what? What's 1 times 100? 1K times 100. It's 100K, right? So this would be Rn. So this is what my signal source. So whatever's driving this amplifier, it's going to have to run this load. What we got? Where did y'all run into this formula at before? Where did y'all see this formula at before? DC, right? You don't remember? This is the reciprocal of the sums of the reciprocal. This is the way we calculate total resistance in a parallel circuit. So that's 100 times 10 to the third. Well, that's 50K, so that'd be 8.3? Good. So this is the path that the signal takes, and you can see them. It comes flying in here, right? We looked at this. It does what? Goes up to that guy. An AC source sees a DC battery as 0 ohms, guys. Then it goes this way, and then it goes that way. Are we okay? We're fixing to do something really interesting that y'all gonna have to do when y'all get to the lab. Is I'm fixing to come over here and add another capacitor. I'm about to make it. It's gonna be hard to do because that's I say I'm gonna come up here. I'm gonna add a capacitor right here. So what's the rule of thumb for capacitors if we size them right? They do what to DC and they do what to AC? So at 30 hertz, but think about it, we're going to operate this thing higher. Let's say 1,000 hertz. This guy right here has almost no opposition to 1,000 hertz. Y'all could do it, but it's going to be 1,000ths of 53 ohms, so it's going to be in the milliohm range, right? So here comes my AC signal. It can either go through that 1K resistor, or 99.9% of it is going to fly over and go around through that capacitor. So this guy right here, we call it a bypass capacitor. Now my DC bias still has to go through the resistor, so it blocks the DC bias, but allows the AC signal to go around. Now, of course, when we calculated our output, our voltage gain, we use RE, but now the AC signal is bypassing RE. So RE don't even come into play anymore, right? You understand that? So how do we get the gain? What does the AC see? Well, the AC sees the dynamic resistance of a PN junction, which is very, very low. So what we have is we have what we call RE, which we usually do in uppercase letters. And RE, of course, is going to be equal to what? RE. And then we have something called RE prime, which I'm going to use lowercase letters because this is AC. This is the signal coming into our amplifier. This is the dynamic resistance of a PN junction. And I have a handout that's in there, but we're not going to use it because what we're going to do is just take for granted. So this is the way RE prime is calculated. As soon as this comes up. So here's all our So they start off with all this math. E is the exponent constant, which is approximately, this deals with common logs, not natural logs. Voltage across the depletion region, the charge on an electron, approximately 1.6 times 10 to the 19 volts. Boltzmann's constants, which is 1.38 times 10 to the minus 23rd joules per degrees Kelvin. Temperature of the device in degrees Kelvin. And then they come up with this big old formula. You follow this? And they come down and they come down and they come down and they come down and do all this math and do this math. And it approximately equals to 25 millivolts over the DC emitter bias. No, it's IE over IE. They just didn't put approximately out there. Because it varies with temperature, but this is close enough for our math, right? You understand that? So it says this thing called RE prime is approximately equal to 25 millivolts over the emitter bias current. So the way we would say it, what was IE? What did we calculate IE to be? Anybody write it down? Yeah, so what would IE be equal to? 400 millivolts divided by 1K. $400 microvolts, right? 400 micrograms. 400 micrograms. So what happens? I want y'all to see this. So I'm going to bring my camera back up. Where's my camera? Looks like I closed it out.